there's another thing that 13.3 does. So here's a little bit more on that. We have this object rotating around, but the x position, we were talking about the x position, is similar to simple harmonic motion. And we already got that the x was a, the hypotenuse, or the radius, sorry, of this disk, or at least of its motion, cosine theta t, and we said that theta t, since it's constant angular velocity, we would have omega, constant velocity is distance over time, right? So constant angular velocity is a change in angle over time, and we solve this for change in angle, and then take the theta initial to the other side, we would get this, and we let the initial angle be 0, so we got that formula there. And then we're going to use that here. So we're going to go back to, since the angular velocity is constant, we were saying that the angular velocity is the change in angular position over time is 2 pi over the period. And 2 pi over the period, well, the period is 1 over the frequency. So 1 over the period is the frequency. The frequency is 1 over the period. So we get 2 pi times the frequency. And I like to think of it like this. If this thing were spinning around at 5 times a second, that would be called the frequency. Okay? If it rotates 5 times a second, how many radians does it move in a second? Well, each revolution is 2 pi radians. So 5 revolutions is 10 pi radians. So when you take that 5 revolutions per second and multiply by 2 pi to get our 10 pi radians per second. And then another way of writing this, if you wanted to, since omega is 2 pi f, we have x is the amplitude times cosine. Omega is 2 pi times the frequency times time. And the book likes to keep it like this. I actually also like this form. I just wish we had some way of doing like x equals a cosine in revolutions ft. I wish we had some way to do this where the cosine is in revolutions, like if it goes around once, we could say, that cosine of 1 is 0, which is not true for radians, right? But that where 1 went all the way around once, but there's no this does not exist. This is what I was saying in class once. This does not exist. Some cosine function you can put your calculator in instead of degree mode and radian mode and revolution mode. So this is true. I think it's helpful, but it's a little bit cumbersome. So a lot of people drop that form. Okay, but we're going to say that that's also, this situation of this x position is similar to a spring bouncing back and forth. So we get the same equation for the spring, and we're going to solve for the velocity or of the mass as it bounces back and forth. And to do that, we're going to go back to page 1, and that same equation you don't have to memorize, but we're going to write that down here. And instead of writing delta x, I'm just writing x. That's what the book writes. Makes it a little easier to look at. So we have this equation, and we're plugging in what's x. X is a cosine omega t. So we have plus or minus root k over m, a squared, and we plugged in a cosine omega t squared. That's x. And then we're just going to do some math with it. So try to see if you can follow along. We're going to pull out the a squared, because there's an a squared and an a squared. Square root of a, the a can come out to be plus or minus a. And we've got inside here, we're going to have a squared times 1, and then a squared times cosine omega t. But 1 minus cosine squared is sine squared. And we can square root the sine squared and just get sine, plus or minus sine, but the plus or minus still stays out here. And then we say, well, root k over m we've actually seen before. If you go back here, omega was 2, sorry, you can't quite see it. Omega is 2 pi times the frequency. So if we use that, we're going to turn the frequency back into the period. So I guess we're really using this. Omega is 2 pi over the period. And the period we had from the page 1 was 2 pi here, and the period is 2 pi root m over k. So the 2 pi's will cancel out. We've got 1 over root m over k becomes root k over m. So that is omega. That was at the bottom of this other page. I just kind of went through that fast in the last video. That's what was down here. Okay, so omega is root k over m, and we've got a root k over m sitting right there. So that is omega. So v is equal to plus or minus omega times the amplitude times the sine of omega t. And I just want to draw a graph of what that means. So suppose that we pull the mass over to the, say to the right here. We're going to move it over here to A and let go. It's going to start out at A, and it's going to oscillate from A back and forth. You know, this is minus A. And then what would the velocity do? Well, right when I let go, it's going to be going, I'm pulling it out over here. It's going to be going 0. But which way does it move when I let go? If I pull it out here, it's going to start to move to the left in the negative direction. So this velocity is going to become negative first. Okay, and it will have a sign. So is it plus or minus? I'm just going to try to make things easier and get rid of the plus or minus. When I let go, it's going to have a negative. So put in a little t here, that velocity is going to be negative. So we can get rid of the positive sign and say minus a omega sine omega t is the velocity. I just switched a and omega. This is actually much easier to prove using calculus. We're trying to get around using calculus, so the proofs take a little longer. I'm going to do one more thing. We're going to calculate or get an equation for the acceleration of the mass instead of the velocity. And we're going to go back to do that. We're going to go back to Newton's second law. We have this object here, F net equals ma. There's only one force on it. I don't know which way the force is right now, but say we've pulled it to the right, the force would be to the left, and it would accelerate to the left. And we're going to take this minus k and delta x equation. I'm going to let the initial position be 0. So when we did this equation, we were letting x0 be the relaxed length of the spring. Wherever this system is at its relaxed length, that's 0. So when we do delta x, it's this minus 0. Because when we derived this equation, the 0 spot is the relaxed length of the spring. So minus k, here's the equation for x, or x final, if you will, equals ma. We're going to solve for a, divide both sides by m, so minus k over m, a cosine omega t. But this k over m, I've seen that somewhere. We said that root k over m was omega, so k over m is omega squared. If you square this, you get omega squared. So this becomes minus omega squared times a cosine omega t, and then I'm just going to switch the a and the omega because that's the way people like to write it. And so this is an equation for the acceleration of the mass as it goes back and forth. You can notice some things from this, particularly, and this should not surprise you. A is equal to minus a omega squared, but cosine omega t is the same thing as that x position. So we're kind of saying a of t is minus a omega squared x of t. So if the position is positive, the acceleration is negative. If the position is negative, the acceleration is positive. That should not surprise you, because if the position is positive, where we called the relaxed length the 0 spot, suppose this is at the relaxed length. Okay. If I pull it to the right, the force is to the left, so the acceleration is to the left. If I move it at all, if it's anywhere over here, it doesn't matter what direction it's going. It could be moving to the left, it could be moving to the right. But if it's over here somewhere, the spring is squished, pushing it to the right, so the acceleration is to the right. So if it's displaced to the left, the acceleration is to the right. If it's displaced to the right, the acceleration is to the left. That should not be surprising. You could have told me that already, I believe. Again, nobody's going to ask you to derive these things, but they are going to ask you to use them. And then so now we'll start working on how to use them in problems.